Hello everyone, it's a pleasure to introduce Nama Ben-David. She's a student from Carnegie Mellon and her advisor is Sky Blalock. And she works on, how she puts it, theoretical foundations for practical concurrent systems. And today she's going to talk about her work on RDMA and theoretical models for it. So I'm very excited. She's also the recipient of a PhD, Microsoft PhD Research Fellowship, yeah. Is that right?
Yeah.
Yes. Did I say it right? Okay. Which is, of course, great. And we're excited to have her here and tell us about what she's been doing. Thanks.
Thank you. Right. So like Sebastian said, my name is Nama. I'm from CMU. And I want to tell you about how we model this technology called RDMA in theory and use that to prove that RDMA is more powerful than previous communication mechanisms. And so I'll actually be talking about the results of two papers, one from PodC this year and one from PodC last year. And this was in collaboration with many great people. Okay. So the first thing I want to do is to tell you what RDMA is. So here, RDMA is a data center technology, and therefore I have this wonderful diagram of a data center. And I want to zoom in on a single connection in this data center and see how that works. So here I have two machines. It's a logical diagram. And each machine at a high level has three parts to it. So it has the CPU, the memory, and the network interface card, or the NIC. And so normally to send a message across the network, what we do is the CPU comes up with the message and forwards it to the NIC, which forwards it across the network and to the other CPU. Okay. Now, RDMA, which stands for Remote Direct Memory Access, again, at a very high level, simply gives us this direct connection between the NIC and its own memory. And so this changes how we communicate a little bit. So if we want, instead of sending messages like before, the CPU can now come up with a message, give it to its own NIC, which forwards it across the network. But this time, it puts it on the memory of the machine directly without bothering the recipient CPU. Okay, and so this is really nice because now we can, a CPU that receives messages doesn't have to worry about slowing down to see these messages. Okay. And so RDMA has been studied a lot in the systems community in the past few years. And so here is just one example which I grabbed from a paper called APIS from 2017. And so we can quickly sort of analyze what's going on here. We have latency on the y-axis, which means that lower is better. And the bottom two implementations here are RDMA-based, and the rest are not. Okay, and what we see, the scale is maybe a little bit hard to interpret, but what we see is a factor of 10 improvement between the worst RDMA algorithm and the best non-RDMA-based algorithm. Okay, and so this is really huge, but there's this question of whether the improvement that we see with RDMA, is it fundamental to what RDMA gives us, or is it just a factor of something else that's going on? And there's some work that casts doubt on whether RDMA is actually fundamentally better. So this was published in NSDI this year. And basically, at a high level, takes the old communication technology and optimizes it and gets raw latencies that are actually very comparable with RDMA.
What is the number of replicas? Is that the number of hops, or is that on the x-axis there?
It's the number of machines. So this is actually replicating, doing state machine replication using consensus. And so it's the number of machines on which we copy the data.
Okay.
And so that table is just latency as in send and receive latency?
Yes. Yes, so it's actually measuring different things, right? So the table is just raw latency of the sends and receives, and here we have an actual algorithm. So it doesn't necessarily mean, that there's nothing to be gained. Right, so the question that we aim to solve in our work is whether RDMA is actually fundamentally better than previous communication mechanisms. Okay, and by better, one way that we can judge whether something is better is by performance, which is what we saw in the previous slide. And there are other ways that we could measure it. So another way is fault tolerance. So we could ask, can RDMA help us tolerate more failures in our system than we could before? And another question is, for example, scalability, right? So can RDMA scale as well as previous networks? And maybe it can scale even better, right? Okay. And so our approach to answering these questions is we take a specific problem, consensus, and we use it as a lens to study RDMA. So we try to see how we can solve consensus using RDMA and whether it's better than before. Okay, and so this is not just some arbitrary pick of a problem, because consensus is really fundamental in distributed computing, because it's used for many applications that we want. So for example, we can use it to replicate state machines across multiple servers. We can also use it to create consistent data structures in shared memory. And then the big one that everyone is excited about is that we can use it for blockchains. So if everybody wants to agree on a common ledger of things that happen. And so what I want to do now is to define consensus more formally, because from here on out in the talk, I'll be referring to consensus algorithms and to bounds, lower and upper bounds on how to solve it. So I want to make sure that we all know what we're talking about. So in consensus, we have many processes in our distributed network, and each one of them receives some input, and all of them have to output something. And so here I have a diagram of the network, and here everybody received some input, either 0 or 1. Now the output actually has some constraints on it. So the first one is that everybody has to give the same output. This is called agreement, right? So for example, maybe everyone outputs 1, and that's a legal value. And the other constraint is called validity. And you should think of it as intuitively, validity prevents us from a priori, before we see our inputs, agreeing on what everybody will output, and then just no communication, everybody will just output that. Right? So the way that we formalize this is we say that the output must be the input of some process. We're not allowed to choose the output from some other set. And for example, here, if everybody had received a 0, then the only valid output would be a 0 as well. Okay, so that's simple enough. That's the definition of consensus. Now, consensus is a little challenging to solve, because in these distributed networks, we often consider other things that go on. So for example, there's asynchrony, which means that we don't really know how long it takes for a message to go across the network. And the other problems is that processes might experience failures. One failure might be a crash, so a process simply stops executing the protocol and maybe doesn't output anything at all. And another failure, which is even worse, is a Byzantine failure. And this means that a process becomes malicious and tries to make us fail our algorithm. And in particular, it might output this wrong answer. Okay, and so we need to relax our definition of consensus a little bit to be solvable. And so, first of all, we only require correct processes to output anything. And secondly, we only require agreement among the correct processes. Okay, so is that clear? Everybody's happy with consensus? Okay,
so just
yeah.
One clarification: when you say output, it's the end of this algorithm, right? Because
Yes.
along the way they may output different values.
Yeah, there's one value, you can think of it as their decision. So they can do this communication, and eventually they declare some output, their decision, and they can no longer change it. Yeah.
And I presume you're going to have to add a fairness constraint too, or probably
so here we won't have any fairness constraints. So I'm not sure what you...
Well, in asynchrony it's possible,
yeah.
but it's not possible for the bit. It's possible.
Right. So if you have a fully asynchronous network, then consensus is never possible. But yeah, we will assume some partial synchrony. So we'll assume that eventually our network is synchronous enough so that we can solve consensus. Yeah. Okay, so back to our main question, we were wondering whether RDMA is fundamentally better than other communication mechanisms. So what I want to do now is talk about what other communication mechanisms we might want to compare to RDMA. Okay, so the communication mechanisms I'll talk about is at a high level two sort of broad categories of communication. One is communicating by message passing. So we have a network, we have machines, they send messages to each other. And this is the application that we've been talking about. So machines might be connected in a data center or might be connected over a larger network. And the other communication mechanism is shared memory. Usually this is done when you have a single machine and it has multiple cores, and the cores can communicate with each other by reading and writing on the same memory. Okay. And so I want to compare message passing and shared memory a little bit and see how they're similar and how they're different. So of course in message passing, if you want to send a message, you send it along your network, the other side receives it. And the challenges are that some processes might crash and that the network might be asynchronous, right? So really there's no way to know for sure whether my message has been received unless I receive some acknowledgement from the other side. Now in shared memory, it's sort of similar. So when I have a message to tell others, I write it on the shared memory, and others might crash, in which case they wouldn't read the data that I wrote. And so I never really know whether others saw my message unless they wrote something back. Okay, so in this way they're similar. I'll now show you some ways in which shared memory and message passing are different. So first of all, note that in message passing, the only real actors in our system are the processes themselves. Whereas in shared memory, we can think of it as we have the processes and we also have this memory that also acts in the system. Now, like I said, to know whether my communication has been successful, I rely on other processes in the message passing network to reply to me. So I need active participation from other processes. Whereas in shared memory, I really only rely on the memory itself. If I know that I executed an operation on the memory and it was successful, then I know that anybody who wants to hear my message will be able to do so. And so really, I only need acknowledgement from the memory. Right? And so this is a strong point for shared memory. Another point is if you think of when you try to broadcast something, and so you send a message to everyone, you need an acknowledgement in message passing from absolutely everyone you sent to in order to know that they all received your message. Whereas again, in shared memory, you only need this single acknowledgement from your memory. Okay? So this is another strong point for shared memory. But there's something that message passing does better, which is that the acknowledgement that you do get can have arbitrary information in it, right? So if a process does respond to your message, it can tell you whatever it wants, right? Whereas in the memory isn't as smart, so it only tells you either if you read then the content of that location, or if you wrote, it's just an acknowledgement. And so this is a strong point for message passing. And maybe it doesn't sound too bad for shared memory, because usually if you communicate on a single machine, it's okay for you to do more operations, more reads, more writes, because they're much faster than it is to go across a network. Right? But you can also think of shared memory instead of being on one machine. Think of having many machines and somehow they communicate over this shared medium. Okay? And in this case, think of these edges as links in a network as well. And so they might have the latency that is just as bad as the message passing latency. Okay? And in that case, the fact that we had an entire round trip and we gained less information from it might really play a role in our performance. Okay? And so this is sort of what RDMA does. So if you remember, we were able to send a message and directly have it go into the memory of another machine. And we can do this with reads as well, so we can request some item and it would be sent back to us. But this is a shared memory-like capability because we don't rely on the other CPU to give us a response, but we also get less information from these responses. Okay, so we're going to compare our RDMA to the previous communication mechanisms, which are message passing and shared memory. Okay, and so now here is the spoiler. This is the takeaway of our work, which is that we show that RDMA does improve upon message passing and shared memory. And in particular, it improves upon the trade-offs that you can get between fault tolerance and performance, and also scalability. Okay, so when I say fault tolerance, I'm talking about, again, we're all in the context of computing consensus. And when I say fault tolerance, I mean either the Byzantine failures or the crash failures of processes. Okay, Now, for performance, there are actually many ways of measuring performance, and we focus on a particular one that we call the common case running time. So the common case is also the best case in most networks. Usually a network is well behaved, it's mostly synchronous, and there are no failures. And so we ask, in such a scenario, how long does it take for the first process to make a decision in consensus? Now, we allow this good scenario, but we require that the algorithm that we're measuring will still be resilient to really bad cases. So we're running these algorithms that are resilient to asynchrony and resilient to failures, and we ask, when everything behaves properly, how long does it take them? Okay, so here is a rough outline of what I'm going to do. I'm going to tell you some more details about RDMA and how it compares to previous results. And then I'll show you how we improve the fault tolerance and performance. And then I'll talk about scalability. Okay, so here I have a table of previous results with our 3 measurements. So I'll talk about fault tolerance, performance, and scalability. So here, these are the results that are known for fault tolerance in shared memory and in message passing. And so I'm using N and F here. N is the total number of processes in our system, and F is the maximum number of failures that we might experience. And what we see is that these are known results, not our own. In shared memory, you can actually solve consensus with everyone failed in your network except for a single person. So here, I'm not even sure if you can see this, but there's a tiny green line here representing the one correct process in your network. And that setting is enough to solve consensus. Whereas in message passing, we need a majority of the network to remain active in order to solve consensus. Okay. Now, in shared memory, Byzantine tolerance has not been really well studied, so I won't talk about any of the results there. But in message passing, it's known that we actually need more of the network to be correct to handle Byzantine failures. So we need 2/3, we need more than 2/3 of our network to be honest in order to solve consensus in this setting. Yes?
So the memory component is assumed to never crash and never attack Byzantine?
Yes, for now. And I'll talk about one setting in which we allow it to crash. Yeah. Okay, right. And to solve these the consensus with this amount of fault tolerance, in shared memory, we actually need 2 round trips. So we need 2 operations to be done. And in message passing, we can get it down to 1. And inherently, this is because in message passing, we can get more information out of our acknowledgements. Okay.
So
yeah.
what's the definition of a round trip in a shared memory? I
Right.
do a read and then a write?
Yeah. So in shared memory, you can think of each operation as counting as a round trip.
Oh, okay.
And the reason behind that is if you think of this shared memory over a network, so you're not actually on a single machine, but you have to access the memory through the network. Then you do one read, you wait for its reply, and you do one write. And so each operation is a round trip. Yeah. Okay. And then I want to talk about scalability, which is a little bit of a fuzzier notion. But shared memory systems usually are on one machine. And usually, these machines don't have that many processes. So you might have tens of processes, maybe hundreds. Some supercomputers might get to thousands of processes, but you don't have too many processes that actually share the same memory. Whereas in message passing, your networks can be really, really large. So you can have networks with tens of thousands or hundreds of thousands of machines. Okay, and so message passing is a much more scalable way of communicating.
Based on which criteria?
Just number of processes that we manage to communicate with.
In a certain kind of latency limit?
Yes.
Reasonable latency?
Yeah, reasonable latency. Yeah, yeah. So shared memory, if we connect more processes to it, things will really slow down. Okay. Okay. And so our results. The first thing I want to talk about is this RDMA setting, where we allow ourselves to use as much RDMA as we want. And what we actually show in our work is that RDMA can get this best of both worlds in terms of performance and fault tolerance between shared memory and message passing. So in the crash scenario, it can get the fault tolerance of shared memory with the running time of message passing. And for the Byzantine scenario, we actually show that it can tolerate more Byzantine failures than message passing can. Okay, But we require all of the network to be connected over RDMA, and so we call this non-scalable setting. And I'll talk more about why that doesn't scale. Okay. Yeah.
Are you assuming that when a process fails, the memory associated, the NIC and the memory associated with that process is still functioning?
So I assume that that we decouple memory and process, and we allow the memory to fail separately. And I'll talk about how the memory fails. Yeah. But in this chart, yes, I only consider process failures. Okay. Okay. And finally, we were wondering how RDMA might be able to scale. And we were able to show that RDMA can, while using few RDMA connections, so basically mostly having a message passing network, we can improve upon the fault tolerance of message passing. And the amount that we can improve, it depends on how many RDMA connections we're allowed to have. Okay. All right, so I want to get into some details about what RDMA can do and what I mean by scalability and all that, and hopefully everything will be more clear. Okay, so here I have my network again. And in an RDMA setting, we can actually choose which connections we open through RDMA. Okay. So for example, P4 here might have chosen these 3 connections to open. And in fact, it can assign a permission per connection. Okay, so it can say P1 only has read access, whereas the others have write access. And it can actually do this at a finer granularity than just the entire memory. So it can divide the memory into memory regions and give different permissions per region. Now the downside is that all of this information must be stored on the cache of the NIC in order for us to be able to use these connections. Okay, and so this is where scalability comes into play, because the NIC's cache is not that big, and so if we have many open connections, we start cache missing, and our latency becomes worse. And so I took this plot. This is a very simplified version of a plot that appeared in the paper called Farm from Microsoft in 2014. And they actually show much more information, but I highlighted one plot line. And the way that we should interpret it is as follows. We have throughput up on the y-axis, and each server on the x-axis actually has several connections open. And we're wondering, and we have a fully connected network, so all the servers are connecting to all the servers. And so really, because we have several connections per server open, the x-axis is just an approximate number of connections open. So in fact, you should multiply this by a factor of about, I think it was 5 to 10. I don't quite remember how many threads they had. Yes?
Are these severe scalability limitations of RDMA fundamental, or are they just an artifact of the first and second generations of RDMA?
Yeah, so that's a good question. I think they are, these specific numbers are just an artifact of the first generation. But I think it is fundamental that to allow these connections, we need to keep this information on a easily accessible cache. And so even if we might be able to grow the cache, we might be able to write this information in a more compact way. But the scalability is fundamental. Okay, so the takeaway just here is that as the number of connections per server increases, our throughput decreases.
Just to follow up on Jay's
Yeah.
point, so this looks very different today.
Yeah.
You can think of going up to 64 machines looks okay.
Yeah.
And then it goes down. Now, how many machines do you have? How
So
many machines do you need?
right. So first of all, again, I think this the number of servers listed here,
Yeah.
they have many connections open per server. So I think really these numbers are, if you multiply them by 5 or 10, is the numbers that really should be reflected. Okay, so I'm studying consensus, and usually most applications of consensus, other than blockchain, don't need that many machines to connect to. But you can think of, we only use consensus as a lens to kind of ask what kind of problems we might be able to solve. And there are many problems that are solved, maybe not consensus, but that are solved across huge networks. And so we also want to understand whether RDMA solutions might be applicable to things like that. Okay, So I talked about scalable and not scalable. And what I meant really is that in the first setting, we allow ourselves to open all-to-all connections over RDMA. Whereas in the second setting, we restrict the number of connections that we allow to open. Okay, so we define this shared memory graph, where it's simply the graph that represents our RDMA connections. And we are able to show that the fault tolerance depends on the topology of the shared memory graph. Okay. So for the rest of the talk, I want to first focus on the fully connected setting, and I'll show you how we improve this trade-off between fault tolerance and performance, and then I'll talk about how to scale. Okay. All right, so first I want to talk about how to model this. Right, so we had this setting, which is what RDMA can do, and now we want to fully connect everybody. And so what we will need to do is keep track of all of this information per node, right? How many regions it has and what are the permissions. And this gets kind of big, especially for drawing the diagram on the slide. And so I'll represent it a little bit differently. So here, this was the representation we used so far, and I'm actually going to decouple memories and processes and represent them separately. And there's actually another reason that I'm doing this, not just for convenience of drawing. But the way that we decouple memories and processes is not quite aligned with how machines decouple memory and process. So we do allow memories to do some computation, some limited amount of computation. And you can think of this as the memories can execute kernel-level code. And the key point here is that processes are allowed to execute user-level code, but the memory code will not be corrupted by a Byzantine process. Okay, so we actually assume that memories might crash, but they will never become Byzantine, whereas their processes might. Okay, so to be more precise about our model, we've decoupled memories and processes. Maybe we have n processes and a different number m of memories in our system. And each memory has a split into memory regions. Okay. Now memories, we allow them to fail by crashing. And when a memory crashes, all of its regions become unavailable at once. Okay. Whereas processes, they might fail by crashing, or they might become Byzantine. Okay. Now processes are allowed to access memories through 3 operations. So the normal ones, it can read a memory and it can write into a memory. And then there's a special one, which we call change permission. And so a process is allowed to request a permission change from a memory and send that request. And now the memory, when it receives such a request, it has some policy that we can specify that it uses to decide whether to grant this access. And so, for example, P6 sent this request, and maybe giving P5 write permission is allowed by our policy, and so this will be granted. Whereas if somebody asks for a request that isn't allowed by our policy, then the memory can simply ignore it and not respond. Okay, so the first thing I want to do is to treat memory crashes. And the way that we do this is very simple. We use standard replication techniques. Okay, so we treat all the memories the same. We have all-to-all connections. And whenever a process wants to access a memory, whatever it is, whether read, write, or change permission, it will send this request to all of the memories at once, and we'll wait to hear a response from a majority of them. Okay. And what effectively happens here is that because we treat all the memories the same, and we only require a reply from a majority, as long as a majority of our processes of our memories haven't crashed, we really change this from an abstraction where we have many faulty memories. We can think of it as an abstraction in which we have a single non-faulty memory. Okay. And this holds as long as we have a majority of the memories correct. Okay, and so I'll actually update my diagrams to make them even simpler, and I'll be drawing just a single memory. And we'll assume that this single memory doesn't crash, and we're allowed to do this because of our replication technique to deal with memory crashes. Okay, and so that was a bit about how we model things, and so I'll quickly talk about how we achieve this crash fault tolerance that's as good as shared memory, but gives us the speed of message passing. And the way we do this is we rely on Paxos. So I want to just give a very brief overview of how Paxos works.
Can you go back to the previous
yes.
slide? So once you assume
yeah.
The
This one?
Once you see, but this picture looks very much like shared memory.
Yes.
And
Yes.
in the shared
So-
memory, the memory cannot fail.
Yeah.
And so the results from shared memory should directly apply.
Yes.
Is that okay?
Yes, they do, right? So remember, what you've just noted is making it very obvious why we can get the fault tolerance of shared memory, right? And so what I'll actually show is why we can get the speed of message passing using this model. Okay. Okay. So the way that we'll do this is we'll rely on the Paxos algorithm. And so I just want to give a quick overview of how it works. Paxos proceeds in 2 rounds, and it's a message passing consensus algorithm. In the first round, if you want to propose your value to be selected, then you tell everybody, hey, prepare to hear my value. Please be ready to hear it. Okay, and then everybody, or like a majority, has to respond saying, okay, I am now ready to hear your message. And after you hear a majority of responses, then you go to the second phase, which is the accept phase. And in this phase, you actually send your message. And if people were prepared to hear it, then they will accept it. That's the high level of how Paxos works. And it seems a little silly because it's unclear why we would need such a prepare phase. And the reason for that is because if multiple processes try to send their value at the same time, we need some mechanism to decide who you listen to. And the mechanism that Paxos uses is that you will only accept the value from the last person who prepared you to hear their value. Okay. And so Paxos actually might never terminate if the network is asynchronous and if timing is really bad. But usually we have good timing, and so everything works out. Now, the way that Paxos, that we can abstract the timing is through a leader election mechanism. So in Paxos, we might think of choosing one leader, and that leader is the only one who is allowed to propose a value. Okay. Now, we can actually do this a priori. So before the algorithm starts, we can all say that the process, say, with the lowest ID will be the first leader. And if that process is slow, then we have some mechanism to overthrow the leader. But if it isn't, then everybody can be prepared to hear this, the message from the original leader, and then that leader can skip the prepare phase. Okay, and notice that each phase is only 1 round trip. And so in the best case where we chose the leader and it is active and it sends the message, we can actually solve consensus using Paxos in 1 round. Okay. So now we want to look at something called disk Paxos, which was introduced by Gaffney and Lamport in 2002. And the idea of disk Paxos is, at a very high level, that we want to run Paxos on shared memory. Okay, and so whenever Paxos would send a message, we would write our value on our disk. And whenever Paxos receives a message, we would go and read the disk. Okay. And in fact, in disk Paxos, our fault tolerance is like shared memory, so we can tolerate everybody but one process failing. Whereas in message passing, the message passing version of Paxos is half of the network failing. Okay, and so now we're going to ask, how does disk Paxos behave in common case, so best case executions, right? So in executions where the network is synchronous and nobody crashes, how does it behave? And remember that we said we can avoid the prepare phase of Paxos if the leader is good. So the leader will simply send its value and then wait to hear acknowledgements from everybody. Okay, and so in disk Paxos, this amounts to writing your value on the disk, and then going and reading the value from the disk to see that indeed you were the only one who proposed the value. Okay, and you do have to check, because remember that while we are considering what happens in the best case, the algorithm itself is not allowed to know that it will experience a good execution. So we do have to check, and so this amounts to 2 round trips, 1 to write and 1 to read. Okay, and so we've seen Paxos and how it achieves 1 round trip, and we've seen that in disk Paxos, it takes two round trips. Okay, and so our idea is to try to get rid of the second round trip while using disk Paxos. And the way that we'll do this is using this dynamic permission mechanism that we have with RDMA. Okay, and so the idea is that we start with the permissions as follows. So the memory at any point in time, gives exactly one process write permission, and everybody else can only read. And so we give a priori our chosen leader, we give it permission. Okay. And so if the leader has permission, it can write on the memory and everything is great. Now, if anybody else wants to overthrow the leader, the first thing that they need to do is to request permission. And they request this, and then the memory can grant them permission, but it will revoke it from the leader. Okay, and if that happens, then P1 might try to write, but it would fail. And so in this case, it would actually only lose its permission if it was contended for the leader status. Right? And so in fact, if it didn't lose permission, it knows that nobody contended with it. And so it can drop the second check. In the good case where it didn't lose permission, we don't need to check that it was alone. And so that is how we reduce 2 round trips back to 1. Okay, so that's the idea of our crash consensus algorithm. I'll briefly overview how we achieve the high fault tolerance for Byzantine. And it's as follows. So in the Byzantine setting, we have 2 pieces to our algorithm. The first is, we call it cheap quorum. And what it does is it very quickly either decides the value or sees that things have gone wrong and aborts. And so we managed to get this speed using a very similar idea. We use this, these dynamic permissions to cut round trips. Okay, and so cheap quorum simply manages to recognize if the network is asynchronous or if there's Byzantine failures, and it will abort in those cases. In which case, we have this algorithm that we call the robust backup that comes and takes over. The robust backup is simply a Byzantine-tolerant algorithm, but it's not fast in any way. And it has this high fault tolerance. So the idea is that if everything goes well, then cheap quorum gives us decision really quickly, and otherwise we have this robust thing that takes over. And the robust backup actually doesn't use the dynamic permissions, but instead it uses the shared memory and the idea that our memory regions are protected. Okay. And so the way that we increase our fault tolerance is by preventing a behavior that's called equivocation in Byzantine algorithms. And equivocation at a high level is simply when there's a Byzantine process and it sends different values to different processes, and they have no way of knowing that this happened. Right? So the Byzantine process basically pretends to each one of them that it only sent one value. And what we show is that using the protected memory regions in RDMA, we can prevent this behavior. Okay? And there's a paper from 2012 by Clément et al. That shows that if you can get rid of equivocation, then you can solve Byzantine agreement with the desired fault tolerance. And so I'll just really quickly overview how we prevent equivocation. And the idea is that we split the memory into these protected regions, and each region allows exactly one process to write, and everybody else can read it. And the permissions are not allowed to change. Okay, and so the idea now is that whenever you want to write on the memory, you write your value and you also sign it. And whenever you want to read, you read the value, but then you also copy it over to your own slot, and you append your signature. Okay, and in this way, anybody else who now, say, reads P1's value can verify that P3 saw the same thing. And in this way, we can prevent equivocation. So we basically can always verify that everybody else heard the same message. Okay, and that's basically it. So that's the intuition for our Byzantine algorithm, and we've seen how we managed to get this good trade-off. Okay, and what we also saw is that we allow half of the memories to fail. And still all the results go through. Okay. So now I want to zoom back out a little bit and remember our main question. We were wondering whether RDMA is fundamentally better than previous communication mechanisms. And our answer is yes. So RDMA can give us the power of shared memory in terms of crash fault tolerance at the cost of message passing. And in fact, we can actually get better Byzantine fault tolerance than either of them could do. Okay, so we saw performance and fault tolerance were great, but we used all-to-all connections, so scalability was iffy. And so now our question is, well, can we preserve these advantages, but also manage to scale? Okay. So this is the question that we'll be addressing next. And to do that, I want to first remember why we were saying that this doesn't scale. Right, so we opened all-to-all connections, we had many connections. We said that this means that the NIC will have frequent cache misses, which slows down the entire network. Okay, and therefore we have slower communication. And so our solution to that is, well, maybe don't open all the connections, right? So we have some incomplete RDMA graphs. Okay. Now what I also want to note is the NIC actually only has to keep track of its own open connections. So really what slowed us down is that we had many connections per machine. So if we consider the graph of open connections, our shared memory graph, really what we want to ensure is that we keep the maximum degree of that graph low. Okay. And so this was all of the features that we said RDMA has. And to study this incomplete graph scenario, we're actually going to really simplify things. And so we won't consider permissions or memory regions. We'll just assume that any open connection allows reads and writes for everybody. Okay, and further simplifying assumption is that we don't allow Byzantine failures, and we also, for now, assume that no memories crash. Okay. Okay, and so this is our model. We call it the M&M, which stands for message and memory model. And it works as follows. We have our asynchronous network with our processes, and they might fail by crashing. Okay, and we also, they are all connected over a message passing network, so they can still send all-to-all messages. Okay, but we also have this shared memory graph. And then the shared memory graph, an edge simply means that the two sides can read and write each other's memories. Okay, and the key that I want to emphasize again is that we actually don't allow memory failures. So even if a process crashes, we assume that its memory is still available for use to anybody who had an open connection to it. Okay. So in this setting, we're actually only really zooming in on the top row of our table. And so we want to understand whether we can get better than the message passing fault tolerance by not connecting the entire network. So the idea of how to do this is as follows. We're going to run a message passing algorithm, but pretend that more people are alive in the network than actually are. Okay? And the idea is that the message passing algorithm can tolerate up to half of the network crashing. And we will communicate with our shared memory neighbors and represent them in our algorithm. And we can do this by running shared memory consensus with them. And note that because shared memory only needs one live process to solve consensus, we can do this even if all of your neighbors are dead. You can still communicate with them and then represent them in the algorithm. So here, for example, if P2 wants to simulate its neighbors in some message passing algorithm, it goes and agrees with them on what their value will be for this round, and then sends this tuple saying, this is my value, this is my neighbor's value, and this is my other neighbor's value. Okay. And in this way, we basically simulate dead people. And so let's see how much fault tolerance we actually gain. So remember, if we have an algorithm running on just a message passing network, and 3 out of 6 people have crashed, then we know from previous bounds that we can't solve consensus. Okay. Whereas in this message and memory network, we might be able to overcome that, right? So we could simulate these 3 live processes, and we could also simulate the dead neighbor of a live process. And so here we've actually simulated 4 out of 6 processes, which is enough to solve consensus, right? But notice that this actually really depended on where the crashes happened in our network. And in particular, if the crash happened at the top of the network rather than the bottom, we wouldn't have been able to simulate that process. We wouldn't be able to simulate its neighbor either. And so we're back down to 3 out of 6, which is not enough. Okay. So the key point here is that we really care about the number of neighbors that correct processes have. Okay, so in order to have high fault tolerance, any possible set of correct neighbors correct processes has to have many neighbors. And so for this, we're actually going to use something called expander graphs, right? So This is a well-studied class of graphs, and basically, if I say that a graph G has high expansion, what it means is that every subset of its vertices has many neighbors. Okay? And a bit more formally, this is the definition of expansion. So we compare the size of the neighborhood of a set S to the size of a set S itself, where S is a subset of the vertices. And this is the expansion ratio of that set. And then the expansion of the graph is simply the worst such set, the set that has the least neighbors coming out of it. Okay. And so we can think of this set S as our set of live processes. The adversary who tries to get our fault tolerance to be as low as possible will pick the set S with the worst expansion. But if we can guarantee that every set has high fault tolerance, then we can guarantee that the entire network will always tolerate many failures. And so in our paper, we formalize this, and we show that the number of failures we can tolerate is actually a function of the expansion of the shared memory graph. Okay. And in our paper, we also show an impossibility result that says the relationship to expansion is inherent. And the impossibility result is not quite tight, but they do both. They are both in terms of expansion. All right, so that was our
Are there results that show that if you limit the degree of vertices, this is the maximum expansion you can get?
Yes. Yeah. So right. So I didn't have it here. You can get. So I think I used a specific expander construction in which the degree is actually constant. So I believe the degree was something like 8, and so regardless of the size of your network, which is really useful. And the expansion was not very high in that case. So I think plugging it in, we got something like we can tolerate, instead of half of the network, we could tolerate 0.55% of the network crashing, or something like that. But as you allow yourself to go past a constant degree, this can raise. Yeah. Okay. And so so we've seen this last column. So this is basically what I wanted to show you. I just want to zoom back out. This was the question we were trying to answer in this last part. We were wondering whether RDMA can keep some of its advantages and still scale better. And our answer is yes. We can certainly tolerate more crash failures of processes than message passing could. Okay, but the advantages that we saw were not just in crash scenarios, right? So we had crash tolerance. We also saw that RDMA helps with Byzantine-fault-tolerance, and we also saw that it helps in performance. And we haven't actually studied these. So while we know that we can scale for crash tolerance, we don't know about performance in Byzantine. I do believe that we should be able to get similar results in these, but we have not worked out the details. So that's an interesting open question. Zooming out one step back, we were saying that we know that when we do connect everybody, then we have this advantage of performance versus fault tolerance. And in consensus algorithms, which I think you pointed out, usually our network size is not that big, right? So we can ask, well, can we take our theory and actually implement it in practice and see algorithms that are better, faster than what we could do before for consensus, and also have higher fault tolerance? And so we're working on implementing that, and our preliminary results are promising, but we're still working on it. And finally, we only studied RDMA through the lens of consensus, but a very natural question is, well, can we, take the advantages that we saw in consensus and apply them to other problems? And so with that, that's all I wanted to say. So I'll be happy to take any questions. Yeah.
So I normally think of the benefit of RDMA over traditional message passing as the fact that you have this fast channel, but it sounds like you're pointing out that the fundamental benefit of RDMA is that it provides another protection domain. It provides something akin to a trusted module, something that you might think of implementing with an enclave. You can instead implement with treating the memory as a trusted, perfectly secure, and in some cases incapable of crashing component.
Yes. Yeah. And so our results are actually independent of the actual latencies of sending and receiving messages.
So some early implementations of RDMA have not been terribly secure. They used keys that were laughably insufficient. Is RDMA now worthy of being considered a trusted module?
That's a good question. So I guess you're wondering about the Byzantine tolerance, right? Because in the Byzantine
That's
scenario,
one thing. I also wonder about its immortality, because
right.
NICs
So
also can fail.
Yes, for sure, NICs also can fail. And I didn't actually address this, right? So I said that we can scale better than message passing, but I assume that the memories don't crash. Now, there's a paper, I think from 2015 called DARE, that did some study of what types of failures do we see in a network. And its conclusion was that about 50% of the time, the CPU fails without the NIC. And of course, the other 50%, the NIC might fail also. And we didn't address this, but I think that our scalability results could actually generalize to memory failures as well. It will slightly change the bounds, though. So I think we can handle some NIC failures, but the point is that CPU failures that leave the NIC active do exist. So I do think that it's a true benefit. And you were also asking about the Byzantine tolerance. And I can't say that I quite know the answer to that. I know that the security is improving, but I'm not an expert on these security protocols. So I don't want to guarantee that, I can always, it's fault-proof and nobody can break it. So, yeah.
There's a student at UW who's working on that. So you might
Okay.
want to talk to him.
Yeah, I'd be happy to. Yeah. Yeah.
So I'm just curious, is you or someone else in CMU actually implementing these ideas right now? Or?
Yeah. So we're implementing. I'm working on an implementation, and it's actually joint work with people at EPFL. So we're implementing. Currently, we have a running implementation of the fast crash-tolerant algorithm that has fully connected network and can get the speed of message passing. And the current really preliminary results show that it's about twice as fast as previous RDMA-based consensus implementations. And we haven't yet implemented the Byzantine algorithm, but that's next. So, yeah.
Any other questions? Okay, now let's thank the speaker.